Comes with lambda iteration method. Lambda iteration method of solution for the all thermal dispatching problem neglecting losses. We can approach the solution to this problem by considering a graphical technique for solving the problem and then extending this into the area of computer algorithms. Suppose we have a three machine system and wish to find the optimum economic operating point. One approach would be to plot the incremental cost characteristics for each of these three units on the same graph. In order to establish the operating points of each of these three units such that we have minimum cost and at the same time satisfy the specified demand, we could use the sketch and a ruler to find the solution. That is, we could assume an incremental cost rate lambda and find the power output of each of the three units for this value of incremental cost. The three units for this value of incremental cost, of course, our first estimate will be incorrect. If we have assumed the value of incremental cost such that the total power output is too low, we must increase the third value and try another solution. With two solutions, we can extrapolate or interpolate the two solutions to get closer to the desired value of total received power. By keeping track of the total demand versus the incremental cost, we can rapidly find the desired operating point. If we wished, we could we could manufacture a whole series of tables that would show the total power supplied for different incremental cost level and a combination of units. That is, we will now establish a set of logic rules that would enable us to accomplish the same objective as we have just done with ruler and graph paper. The actual details of how the power output is established as a function of the incremental cost rate are of very little importance. Procedure is iterative type of computation and stopping rules are used. One is stopping rules based and finding the proper operating point within a specified tolerance. Second is stopping rules based on maximum number of iteration. We could, for example, store table of data within the computer and interpolate between the stored power points to find exact power output for a specified value of incremental cost rate. Another approach would be to develop an analytical function for the power output as a function of the incremental cost rate. Store this function or its coefficients in the computer and use this to establish the output of each of the individual units. This procedure is an iterative type of computation. Base point and participation factor assumes that the economic dispatch problem has to be solved repeatedly by moving the generator from one economical optimum schedule to another as the load changes by a reasonably small amount. We start from a given schedule, the base point. Next, the scheduler assumes a load change and investigates how much each generating unit need to be moved in order that the new load be served at the most economic operating point. Assume that both the first and second derivatives in the cost versus power output function are available. The incremental cost curve of the first unit is the load changed by an amount for a small change in power output on this single unit. This computer implementation of such a scheme of economic dispatch is straightforward. It might be done by provision of tables of the value of as a function of the load levels and devising a simple scheme to take the existing load plus the projected increases to look up these data and compute the factor. Somewhat less elegant scheme to provide participation factor would involve a repeat economic dispatch calculation at the base point. Economic generation values are then subtracted from the new economic generation values and the difference divided to provide the participation factor. These schemes work well in computer implementation where the execute on time for the economic dispatch is short and will always give consistent answers when units reach limits. Pass through breakpoint and piecewise linear incremental cost function or have non-convex cost curves. Next topic is we will see unit commitment. The lifestyle of a modern man follows regular habits, and the present society also follows regularly repeated cycles or pattern in daily life. Therefore, the consumption of electrical energy also follow a predictable daily, weekly, and seasonally pattern. There are periods of high power consumption as well as low power consumption. It is therefore possible to commit the generating units from the available capacity into service to meet the demand. The previous discussion all deal with the computational aspect for allocating load to a plant in the most economical manner. For a given combination of plants, the determination of optimal combination of plants for operation at any one time is also decided for carrying out the aforesaid task. The plant commitment and unit ordering schedule extend the period of optimization from a few minutes to several hours. From daily schedule, weekly patterns can be developed. Likewise, monthly, seasonal, and annual schedules can be prepared taking into consideration the repetitive nature of the load demand and seasonal variations. Unit commitment schedule are thus required for economically committing the units in plants to service with the time at which individual units should be taken out from or returned to service. Constraints in unit commitment. Many constraints can be placed on the unit commitment problem. The list presented here is by no means exhaustive. Each individual power system, power pool, reliability council, and so forth may impose different rules on the scheduling of units depending on the generation makeup, load curve characteristics, and such. Spinning reserve is the term used to describe the total amount of generation available from all units synchronized on the system minus the present load and losses being supplied. Spinning reserve must be carried so that the loss of one or more units does not cause two for a drop in system frequency. Quite simply, if one unit is lost, there must be able reserve on the other unit to make up for the loss in a specified time period. Spinning reserve must be allocated to obey certain rules, usually set by a regional reliability council in the United States, that specify how the reserve is to be allocated to various units. Typical rules specify that reserve must be a given percentage of forecasted peak demand, or that reserve must be capable of making up the loss of the most heavily loaded unit in a given period of time. Others calculate reserve requirements as a function of the probability of not having sufficient generation to meet the load. Not only must the reserve be sufficient to make up for a generation unit failure, but the reserve must be allocated among fast responding units and slow responding units. This allows the automatic generation control system to restore frequency and interchange quickly. In the event of a generating unit outage beyond spinning reserve, sorry, the unit commitment problem may involve various classes of schedule reserve or offline reserve. This include quick start, diesel or gas turbine units, as well as most hydro units and pumped storage hydro unit that can be brought online, synchronized, and brought up to full capacity quickly. As such, these units can be counted in the overall reserve assessment as long as their time to come up to full capacity is taken into account. Reserves finally must be spread around the power system to avoid transmission system limitations, often called bottling of reserves, and to allow various parts of the system to run as island should they become electrically disconnected. Thermal unit constraints. Thermal unit constraints usually require crew to operate them, especially when turned on and turned off. A thermal unit can undergo only gradual temperature changes, and this translates into a time period of some hours required to bring the unit online. As a result of such restriction in the operation of a thermal plant. Various constraints arise such as minimum uptime, minimum downtime, crew constraints. Minimum uptime is once the unit is running, it should not be turned off immediately. Minimum downtime, once the unit is decommitted, there is a minimum time before it can be recommitted. Crew constraints, if a plant consists of two or more units, they cannot both be turned on at the same time since there are not enough crew members to attend both units while starting up. In addition, because the temperature and pressure of the thermal unit must be moved slowly, a certain amount of energy must be expended to bring the unit online. This energy does not result in any megawatt generation from the unit and is brought into the unit commitment problem as a startup cost. The startup cost can vary from a maximum cold start value to a much smaller value if the unit was only turned off recently and is still relatively close to operating temperature. There are two approaches to treating a thermal unit during its down period. The first allows the unit's boiler to cool down and then heat back up to operating temperature in time for a scheduled turn on. The second requires that sufficient energy be input to the boiler to just maintain operating temperature. The cost for the two can be compared so that if possible the best approach, cooling or banking, can be chosen. Up to certain number of hours, the cost of banking will be less than the cost of cooling. Finally, the capacity limits of thermal units may change frequently due to maintenance or unscheduled outage of various equipment in the plant. This must also be taken. Other constraints, hydro constraints, fuel constraints. Hydro constraints is unit commitment cannot be completely separated from the scheduling of hydro units. In this text, we will assume that the hydrothermal scheduling problem can be separated from the unit commitment problem. We of course cannot assert flatly that our treatment in this fashion will always result in an optimal solution. Must run, some units are given a must run status during certain times of the year for reason of voltage support on the transmission network or for such purpose as supply of steam for users outside of steam plant itself. Then fuel constraints. We will treat the fuel scheduling problem in which some units have limited fuel, else have constraints that require them to burn a specified amount of fuel in a given time. Presents a most challenging unit commitment problem. Thank you.